All right, hello everybody. My name is Stephen Hummel. I am our dark sky specialist here at McDonald Observatory in the University of Texas at Austin, and I'm joined today by Stephen Odewahn, one of the many other Stephens here at McDonald Observatory. There's quite a few of us. Sometimes it gets a little hard to tell us apart. But Stephen Odewahn is a resident astronomer here at the Hobby-Eberly Telescope, our largest telescope here at McDonald Observatory. And so, unlike me, he is a professional astronomer, and he's here to talk a little bit about what it is he actually does here, and his research and more. Just generally have a good conversation. That's our goal. Stephen, why don't you just first start us off by telling us how you got interested in astronomy? What made you choose astronomy as a field?
Well, I was always interested in the sky, it seemed, even as a child, but I'll show my age a little bit here because I've wondered about this. I was always fascinated with looking at the sky and seeing stars all over the place or seeing the moon. Um, but when I was a really young child, I was about 3 years old. My mother one day was extremely excited and she had the television on and she sat me in front of the television and she said, "Oh, this is something really spectacular that's happening. Commander Alan Shepard is going to go into space, and you have to watch this. We're going to watch it." And I saw the rocket go up, and I think it was her excitement. And I must have asked, what space, or what are you talking about? And actually, it was years later. It was when I was 7 or 8 years old, when I finally realized that, oh, Commander Alan Shepard, that was not the rocket thing going up. That was the guy inside the rocket. I mean, I was just a little kid,
It's a big
but
difference.
I'm sure that interaction probably influenced me. I was always fascinated with things in the sky, and I got a telescope when I was in the second grade, and I built one when I was in the eighth grade, ground the mirror, and so I was always
So you
uh,
built your own telescope in eighth grade.
right.
That's a lot of work.
Well, it was, but it was the only way I was going to get a really good telescope. And in fact, it was in the seventh grade that I was just sort of browsing through the library, and I saw this book by Patrick Moore. You might know that name. He was a very famous British astronomy writer. He wrote a lot of books on amateur astronomy, and uh, and here was this book, How to Make Your Own Telescope. It just completely blew me away. This concept of making your own telescope, grinding the mirror and figuring the parabolic curve and getting something that would work. And so, yeah, as soon as I read that book when I was in the seventh grade, it was like all I wanted to do was build a telescope. And it was another year or so later that I did have a working telescope, and so it was a little 6-inch f8 telescope that I used for years and years. So uh,
Do you still have it?
I have the mirror. The
Hey, that's the
telescope,
heart
the
of it. Yeah.
mounting, all of the stuff has gone by the wayside. But yes, not 20 feet from where I am right now, that mirror is in a box. I mean, then I became a professional astronomer years later and never have any fun anymore with stuff like that. It's always been a dream of mine to build a telescope again and put that 6-inch f8 mirror in there and get it re-illuminized. And so one of these days, but so far I'm too busy, doing the professional astronomy. But one of these days, I'm going to get back to some of the more fun stuff, like actually using a telescope in my yard. So,
Yeah. So where did you go to school for astronomy?
well, I went to school at the University of Alabama as a physics major, but I only studied physics because I wanted to do astronomy, and then I went to the University of Texas for grad school. I have a master's and a PhD from there. Um, it was kind of interesting though. One summer, I guess, when I was a sophomore or junior in college, I rode around to every observatory, to every department, saying, "Hey, you know, I want to do astronomy for the summer. Can I do anything?" And Harlan Smith, who was the director of the observatory at the time, passed my letter on to Gerard de Vaucouleurs, and uh, and that's how I met him. I went to Austin for a couple summers and worked in the department there for him, doing first measuring supernovae light curves off of photographic plates, and then by the next summer, I was writing software to do photometry of stars and resolved galaxies. galaxies that aren't so far away that we can see the individual stars still in them.
Now, today, you are a resident astronomer at the Hobby-Eberly Telescope. So, what exactly does it mean to be a resident astronomer? How's that different than some other astronomer?
Well, the important word there, of course, is resident. It means I live here at the observatory. I'm doing this. I'm talking with you from my home office in the home that the observatory provides for me.
Right. We're actually not that far away, right? Just
No,
social
we're
distances.
we're probably like a few hundred yards apart.
Mhm.
Um, so um I live here at the observatory. We have four astronomers that live here. This is a particularly complicated telescope. I won't go into the reasons why, but the Hobby-Eberly Telescope, the telescope I use, is a rather complicated telescope to use, and so it's easier to operate if you have just a few astronomers that really understand it quite well, and then we do all the observing for, say, 30 or 40 other projects during periods, which we call trimesters, 4 month periods during the year. Um, so there might be 20 or 30, 40 different projects that we can choose from. And then we would choose what should be observed when based on the conditions. Is the moon up? Is it cloudy? All sorts of things like that.
So you're the one who's making the judgment calls of what to observe next with this absolutely massive telescope, right?
That's right.
So the Hobby-Eberly Telescope, for the uninitiated, pictured here, is currently the largest telescope in the world that's operational. And usually, when we're not experiencing a pandemic and such, it's one of the largest telescopes in the world. Um,
That's
but what you do essentially then is decide whose research gets done next, right?
That's correct. That's correct. Based on the conditions. So um, there are panels with each institution. Like I used to be on the panel for the University of Texas. We sort of rotate in and out on this. It's called the TAC, the Time Allocation Committee. That a group of astronomers that read everyone's proposals and they'll rank the proposals based on scientific merit. And so each proposal, each project will have a sort of a grade as to these are the most important projects. But then beyond that, we have to decide based on if it's extremely clear, if it's extremely dark, if the seeing is good. If the turbulence of the atmosphere is low enough that we get nice, tight, sharp images of stars. Then, if we have those conditions, we'll observe certain types of projects, and vice versa. If it's a little cloudy, if the seeing is poor, then we'll choose other projects. So my job is sort of on the basis of those conditions is to decide what science projects get done when.
Right, because there's a lot of variables, right? There's a lot going on that could affect the quality of the data, and so it's not like it could just be easily automated, right? So
Right.
having that human judgment there, deciding what target to look at next based on the conditions, it's not always straightforward. Uh,
It
uh,
isn't. It isn't, and also the mechanical and electronic and computational properties of the telescope can change suddenly, and in other words, things can break down, and you have to adjust on the fly. Uh, at least sometimes it's for an hour or two. Sometimes it can be all night. Something has to await for the next day to be fixed, and that's very common, especially with these large 10-meter class telescopes. I mean, they are very uh, fragile, most of them, very complicated machines. And so you have to, from night to night, you have to adjust your operational procedures just based on, what's acting up on the machine, software wise or hardware wise.
so what does a typical night look like? Like when you're doing your job at the Hobby-Eberly Telescope, what are you actually seeing? What are you looking at?
Well, again, that depends on the conditions. Like I had just finished a 4 night run the night before last, and the moon is waxing now, which means it's getting brighter. If you look, at sunset tonight, you'll look over and you'll see the moon is still less than a quarter illuminated, and getting brighter and brighter as time goes on. But that means 4 or 5 days ago, the sky was mostly dark at night, and so on those nights, I was mostly observing what we call het fields. Het stands for HET dark energy experiment. So, and there we're using a new spectrograph on the telescope called Virus.
You
Very
just you just
timely
used
name.
a very big word there. You used spectrograph.
Ah,
So let's
right.
back up there. What exactly? So you're not taking pictures of things with the telescope, right?
We
So
take pictures, but only to line up our spectrograph to make sure that the targets that we are interested in are falling properly on this instrument that we call the spectrograph. Good to stop me. And
yeah.
you had a diagram of that, right?
Right, yeah. So, but you're sitting in the control room, right? You're staring at a bunch of computer screens, and then what you're doing is you're using this device called a spectrograph, right? And pretty much all of modern astronomy now is spectroscopy, or at least almost the largest component of it is. But yeah, why don't you talk a little bit about what exactly a spectrograph does?
Well, it splits the light up. The simplest spectrograph is something we see in the sky quite a lot, which is the condition when raindrops split sunlight into a rainbow of colors. And so we've known about that phenomenon for hundreds of years. And then about 300 years ago, a fellow named Isaac Newton, who pretty much figured out everything that was worth figuring out back in the day, he figured out, oh, I can use something called a prism that will act just like a raindrop, and it will take the light from, say, the sun, and it will break that light down into its constituent colors. And of course, Newton was just discovering that, oh, white light is just a combination of all these different colors of light. That was one of the many great contributions of Isaac Newton. But and then later there was a fellow named Fraunhofer, Joseph Fraunhofer, who figured out that, oh, I can add a little bit more optics, something called a collimator and something called a telescope. But and then in the center of that, there's this thing which in Fraunhofer's case he used a prism, but it breaks the light from any object that we're seeing, whether it's a star or a planet or a light bulb. Um, and it breaks it into its constituent colors. And that rainbow of colors, of course, scientists, we always like fancy pants names for things. So we call that array of colors the spectrum of the object. And you can do quite a lot of physics with the spectrum of an object. Yeah. So,
Yeah,
uh,
so we can learn a lot more than a picture could tell us. Like a picture could tell us, spatially what something looks like, but a spectrograph can tell us what something is made out of, and a lot more
right.
information.
Right. In fact, there was when I taught at the University of Minnesota, the big introductory astronomy class, people were always fascinated with the fact that with spectroscopy, how important it was. And then one of the main things was um, you can use it to find the more or less the chemistry, say, of the stars. And it was interesting because about 200 years ago, there was a French philosopher. I can't remember his name now, but he was theorizing what are some of the problems that we'll never know the answer to. And one of the things that he decided was an unknowable fact, was the compositions of stars. And this was about 50 or 60 years before Fraunhofer. It was about the Romantic period, the early 1800s. Um, but because Fraunhofer came along in the sort of the later, the 1830s, 1840s, and built the first spectroscopes. And so this, you know, basically 30 or 40 years after this philosopher formulated that an impossible problem to solve was the compositions of stars, well, spectroscopy
Solved it,
provided
yeah.
the way to do that. And because you can look at the light coming from the star and split it up into its spectrum, and different elements have different types of spectra. And so we could find that, oh, gee, most of the stars they shine with the light of hydrogen and helium, carbon, oxygen, all these other types of things that chemists at the time were starting to understand. Oh, these are present on the earth, and oh golly, look, they're also present in the stars. So it really was a great expansion of the capability of the field of astronomy and physics. um, and then later it was discovered that you could do things like measure the masses of objects, the velocities of objects, how quickly they they turn on their axes. There are all sorts of things we can do with spectroscopy that we use that for today.
Yeah, an incredibly powerful tool, and that's basically what the HET was designed to do, right? It was designed to do spectroscopy and a lot of it. And
That's
so,
right.
when you're talking about HET before, what you're doing is you're taking a bunch of spectra across a huge area of the sky, right?
That's right. That's right. We're doing a combination. We're doing a survey for galaxies, and these have been done for 50 or 60 years, these types of surveys. But the new thing, what people used to do, and I've worked actually on several of these large surveys, uh, you would have a digital sky survey or a survey of like basically photographs or digital images of the whole sky, and you would analyze those and find where the stars and the galaxies are. And most people are interested in both, but in particular, in the last 30 or 40 years, people have been interested in galaxies and the properties of galaxies and their distribution in space. So you would do these big digital imaging surveys and find the galaxies, and then you would go with a telescope and with a spectrograph on that telescope and measure the spectra of those galaxies one at a time. So it's really two surveys, a digital imaging survey and a spectroscopic survey. But the thing that we're doing now with this virus, and you hit the key point there, it's taking many spectra at one
And
time.
virus, we're not talking about the thing with the letter C, right? But we're talking about an instrument that happens to have an unfortunate name.
At this time, it's a
Yeah.
very unfortunate name, yes. And I won't even, it's an acronym. I won't, and practically even the fellow that built it probably doesn't know all of the words anymore in the acronym. But so it's the name of a spectrograph, but it uses something called a fiber bundle. Um, it basically it gives you a spectra of many little positions on the sky.
So you're looking at these incredibly distant galaxies, right? And they're emitting this ultraviolet light, just a little bit of it, which because of the expansion of the universe is shifted to become visible light, right?
That's right.
But why are you looking at these incredibly distant little galaxies? What's so interesting about them?
Well, what's interesting these days, and really for the past 15 or 20 years, the big problem in astronomy these days um, is something called dark energy. And let's back up for a minute here. Uh,
The big
a man
topic.
named Edwin Hubble, back in the about 90 years ago, Hubble came out with a paper, and actually a number of people had kind of realized this before, but Hubble's name is really associated with this. That what he found observationally was that the universe is expanding, and everyone now is pretty familiar with that concept that when you look at a galaxy, the further and further away that galaxy is, the faster it appears to be receding from us. And all of the galaxies which are very distant, they're all receding away from us. And so this is the expansion of the universe. Well, about 20 years ago, in fact, a fellow that I used to work with at the University of Minnesota, we were postdocs together there. He went off to Lawrence Berkeley Labs, and he worked with one of these groups that discovered that about 20 years ago that the expansion of the universe is actually speeding up with time. That means it's accelerating, and so no one expected that. That was a real surprise, um, and so the concept of how that happens is what really boggles the imagination. I think we were talking about Newton earlier. We were talking about Isaac Newton and his one of the famous equations that he came up with was F equals ma, force equals mass times acceleration. So if you want to have force or energy on one side of the equation, if you want to move mass around on the other side of the equation, to do that you have to have an accelerating um, force, the A part of the equation. And so to have this accelerating universe, we have to have this extra source of energy. And we still, to this day, we don't know the source of that energy. We don't know what's going on, but we know it has to be there if it's going to create this acceleration of the expansion. And so there are a lot of experiments these days, observational experiments, trying to measure the rate of expansion of the
The guest star.
yes, that's Henrietta Leavitt, my cat. Uh,
Which is a great
maybe
name.
we can talk about that later, why she's named Henrietta. But uh, so the goal of these projects is to find very distant galaxies and then study their redshifts. In other words, their rate of expansion, how fast those galaxies are receding away from us, and study the distribution of those galaxies in space to learn something about how the acceleration rate is changing throughout the history of the universe. And so that's why we have to use very distant galaxies. That's what HETDEX is doing, is trying to use these Lyman alpha emission galaxies, to use them as probes, basically. Where are the galaxies and how are they distributed in space at greater and greater distances, which means earlier and earlier times in the universe. And through that type of observation, we'll try to learn something about how this dark energy, how its properties are changing throughout the history of the universe, and then perhaps learn, well, what is dark energy? What is driving this acceleration of the expansion of the universe?
That big questions. Why is the universe expanding? And that's what really one of the biggest projects on the Hobby-Eberly Telescope.
Sure is.
Yeah, but you use more than just you have at least used more than just the Hobby-Eberly Telescope in your career. You've used another very famous telescope which recently celebrated its 30th birthday. We can talk about that a little bit.
Right. Yeah. I've done quite a bit of work with that, with various groups. The Hubble Telescope is what you're referring to.
Yes.
And I've always been fascinated with galaxy morphology. In other words, the different types of galaxies that we see. As I was saying earlier, we see most galaxies are either these big ball-shaped, spherical distributions of stars, or disc-shaped distributions of stars like our Milky Way, or some combination of the two. And so, but there are all sorts of other features. Some of those disc-shaped galaxies have big, bright pinwheel structures. We call them spiral arms, and some of the spiral arms seem to come off of a big linear feature in the galaxy called a bar. And so I've always been fascinated with what are the physical mechanisms that create these different conditions and different types of galaxies. So I've studied that essentially since the time I was a graduate student. And in the 90s, we started using the Hubble telescope to look at very, very distant galaxies, again, because we want to look at, say, some of the youngest galaxies in the universe. And how do we do that? Well, we look at young parts of the universe. And that's what the Hubble telescope gave us the ability to do. We could look at galaxies that were so far away that they had to be sitting in a part of the universe that was, say, half the age of the universe today that we see. You
Right,
know,
because the further away something is, the longer it takes for the light to reach us. So
that's right.
the further away you look, the further back in time you're looking, essentially.
Exactly. And so we can commonly look at galaxies now that, like in the 90s, we were using the Hubble telescope to look at galaxies where we could see all of the detail. We could see if they were early type, like elliptical galaxies, or disk like, what we call late type galaxies, galaxies like the Milky Way, galaxies like M33, or some of these other galaxies that people might be familiar with who are watching this broadcast.
If they've
And,
stuck with us this long, right? They
yeah,
probably.
right. And um, so one of the things we wanted to know was, well, what happens? Which are the types of galaxies that form first? So one thing you can do, and you can't just sit and watch a galaxy live out its life, because they seem to evolve on timescales of billions of years. And the universe itself is about 13.5 billion years old. So what we do is we look at parts of the universe that are progressively younger and younger, and we do that by looking at them uh, further and further away. Basically, the farther away you go, the younger you're looking at. And then we sort of look at the types of galaxies that are in those parts of the universe. And that's kind of where my contribution came. I developed a technique of using what are called artificial neural networks to take the images of galaxies and classify them based on more quantitative methods than just looking at the galaxy and saying, oh, that's an elliptical galaxy, or that's a spiral galaxy.
So,
And
so
so
what you're trying to do with these artificial neural networks is essentially classify these galaxies in an automated way, right? Using computers rather than just looking at each one and
That's
classifying
right.
it visually, right?
That's right. And we want to do that because we want to mass process a lot of data, but we also want a more quantitative uh, method of producing the
Right,
types.
because humans will make errors, right? It's a
Right.
judgment call, whereas,
That's right. That's right.
yeah,
And so, in essence, what we're doing, and again, this is sort of a timely thing. In essence, what we're doing is we're looking at different parts of the universe, different ages in the universe, and we're taking a census of the galaxy population. You know, how many ellipticals, how many spirals, how many what are called irregular galaxies. Like there's a very famous set of galaxies, the Large and Small Magellanic Clouds, that are neighbors of our own galaxy. And they are what we call irregular or late type galaxies. But they're still uh, have this disc-like structure, but it's very ragged. It's not the big, beautiful pinwheel structure that we associate with things like the Milky Way. And so basically, the first thing we started to do was just count up these different types of galaxies and see what happens. And as it turns out, the punchline was back in the day. Um, what we were surprised to find was that there were substantially more of these late type irregular galaxies in the earlier phases of the universe. And then, of course, there are lots of problems with the analysis, but because we're looking at galaxies as we look further and further away, we're looking more and more in the UV part of the spectrum. And does that change the appearance of the galaxy? Well, darn it, yeah, it does. And so we have to account for that in the analysis. We have to change the neural networks so that they can know what what wavelength, what color of light actually they're classifying in. So there are complications, but
but this was done with the Hubble Space Telescope, right? And one of the big
right,
advantages of the Hubble is that it's in space, right? It's above the atmosphere, which means it has a clearer image, especially in the UV, because our atmosphere blocks a lot of UV light, right?
right. And the other light, even in the infrared, the redder colors, um, the light, when it goes through our atmosphere, it gets fuzzed up by the atmosphere. And that gets back to this term that I used earlier, the seeing, basically the turbulence of our atmosphere. If the atmosphere is not nice and steady, then we get big fuzzy images for the stars and the galaxies. And in fact,
This is why
for all
stars twinkle, right? When people see a twinkling star, we astronomers don't like that, right? That's bad
That's
seeing.
right, because we can't see the detail. And so all of these very, very distant galaxies, well, they subtend very, very small angles on the sky. They're only, like most of the galaxies that I was studying with my first studies with with the Hubble telescope, um, those galaxies were only a few arc seconds across on the sky, right?
Tiny, tiny
Well,
things, right?
when you look at faint stars, or actually any star, those are only a couple arc seconds across on the sky. And so, if you took a ground-based image of a lot of these galaxies we were studying with the Hubble telescope, you would not be able to tell even that object was a star or a galaxy. Much less seeing the fine detail in the galaxy image and being able to determine if it's an elliptical galaxy or a spiral galaxy or an irregular galaxy. So that's what the Hubble telescope, by virtue of being above the atmosphere, that's what it gives us. And now we have a whole host of other space telescopes that look, they're optimized not to look in the optical light, but to look in the ultraviolet or the infrared or the X-ray or gamma rays. So they're all looking in different parts of the spectrum, um, the electromagnetic spectrum, we call it. But the fact that they can do that because they're above the atmosphere, and it really is changing astronomy substantially.
So if these space telescopes are so great, then what's the point of a ground-based observatory like us, like McDonald Observatory?
Right? And that's a natural question, and the answer is that most of these space telescopes, like the Hubble Space Telescope, it's a little bit smaller than the 107-inch telescope here at McDonald Observatory. It really, I won't say it's a baby telescope, but by modern standards, the diameter of the mirror that's gathering the light in the Hobby-Eberly Telescope, the Hubble Telescope, um, it's not a very large mirror. It's about 90 inches across, and so it
Right.
doesn't gather a lot of light, a lot of the what we call photons, the particles of light that we use to form the image of an object.
So
And
how
so,
does that compare to the Hobby-Eberly Telescope? So
well, the Hobby-Eberly is about is a 10-meter telescope.
whereas
So
the Hubble is
the
like
diameter
2.4,
of
right?
the, I'm sorry,
The Hubble is about 2.4 meters or so across.
right, right, and
Yeah,
so
and it's more than just 4 times the size, right? Because the area is more like 16 times closer
exactly,
to.
and it's
Yeah.
the area. It goes as the of course the square of the radius, and so the area determines how many photons you're going to gather, from your astronomical object of interest, whether it's a star or a galaxy. And so um, to do things like what we do here at McDonald Observatory quite a lot, what you mentioned was the spectroscopy. That's what the Hubble telescope was built for. There, not only are you trying to look at a faint object, but you're trying to spread the light from that faint object. You're trying to spread it out into all of these different wavelengths. So you're subdividing the photons by their color, by their wavelength. And so you have to have a lot of those photons before you can build up an image of the spectrum. That's why you need the larger gathering power of a 10 meter versus say a 2-meter mirror. And unfortunately, we don't have the technology yet. We don't have the resources to put a 10-meter telescope in space. That of course is what we'd love to do, but so far we can only put um, these smaller telescopes up into space. We're working on the what used to be called the Next Generation Space Telescope. Now it's called the James Webb Space Telescope. That should be launched in the next few years, and that I think will be like a 4 or 5 meter telescope. I don't know the exact
Six and
size.
a half. Yeah. So
Yeah,
and that's a over $10 billion project
right.
just to launch that one telescope, which still won't even be big as the Hobby-Eberly. And the Hobby-Eberly, over its whole lifespan, including upgrades, is only about 60 something million dollars.
Right,
James
right,
Webb is over 10 billion. So you can build a
right.
lot of very large ground-based telescopes for the price of one space-based telescope. You
That's
can,
right. And still, as you noted, I mean, still the this new, very expensive, latest, greatest space telescope, the James Webb Telescope, will not be as large as these large ground-based telescopes. And of course, the big deal these days, now people there are several groups on the planet that are trying to build 30-meter telescopes. That's what we want now.
hmm
And again, it's to gather the light. We'll have problems with the fuzziness being caused in the images by the atmosphere. But the large aperture of these telescopes will allow us to spread the light out into spectra and do quite a lot of physics just from the spectra alone. And so really, these large ground-based telescopes and the smaller space-based telescopes, they work in concert to give us a good picture, a clearer picture of the physics of these astronomical objects. So large ground-based telescopes, they will be important for quite some time until we can start building them on the moon. Then
Yeah.
it would be a little easier mechanically, but then you have the problem of how to get up there to the moon and all the resources to build the
Right.
telescope.
And if something breaks in space, it's a lot harder to fix than if something breaks on the ground, right? And
It,
you can
it's
you can
much
experiment more with on the ground too. If something doesn't work right away, you can easily fix it.
right.
Uh, Do you have any advice for someone who wants to become an astronomer? Someone anonymous asked that question.
Yeah.
If you're thinking about pursuing a career in astronomy, what would you tell that person?
Well, I would say first, uh, maintain your enthusiasm. That just keep connected to the field and experience the excitement that is astronomy. And then I would say the more mundane thing is by the time I was in high school, even junior high school, I started realizing that I had to study, of course, as much science and as much math as I could. And so I started um, taking as much math in high school as I could, and chemistry and physics, of course, and all of that to prepare for being a physics undergraduate, a major, in college, uh, because I knew that I had to study physics if I wanted to study astronomy and become an astronomer. So yeah, try to do as many of the sciences as you can in school. And of course, these days, something that was just getting started when I was a kid, but of course today, um, the ability to use a computer, not just look at things on YouTube, but to understand computer languages and how to program. That's always a valuable skill. So I think that's something new compared to like when I was a kid. Um, Try to understand how to program a computer and make it do the things that you need to do computationally. So all of those sorts of things I think would get you in good stead as far as trying to prepare yourself to become a professional astronomer. But really, I think like many things in life, it's just maintain your enthusiasm. Try to stay connected to those exciting things that I mean, when I was a kid, few things excited me more than looking at the big bright image of a galaxy. I mean, I don't know what it is, but it just really excited me and got me moving um, and got me through a lot of the more mundane things like, learning the quadratic equation or whatever. I
Right.
mean,
Yeah, it all seems very abstract, and then when you actually start to apply it, it makes a lot more sense.
right.
It becomes a lot more interesting too.
Uh huh.
Yeah. All right, I have one last question from you. This comes from Trey Valadez from Alamo Heights, Texas. And we have all been affected in some way by COVID-19. What kinds of changes have you and your colleagues had to make to cope with the pandemic? In other words, how has life at McDonald Observatory been hampered by social distancing?
Well, that's something I've been thinking a lot about uh, because, in many respects, I am sort of naturally socially distanced up here. I've been here for 17 years. I live up here with a few cats, uh, and my wife lives in Arizona. We sort of commute back and forth, but really, it's kind of a isolated existence up here, up at McDonald Observatory. The closest little town of 800 people is about a 15-20 minute ride away. So we've always been fairly socially distanced up here, and when I'm not on the telescope, I might go several days without even speaking to anyone. Which is kind of an odd situation. So in that respect, it hasn't changed my life as maybe radically as most people's lives are being changed now. One thing that is different is that when I would work at night, when I would observe on the Hobby-Eberly Telescope, I would be present up at the observatory with one other person. We have four astronomers here and four telescope operators. And the telescope operator is the person that does all the hard work. He or she, points the telescope and focuses and does all the stuff. We just sort of, the astronomers, we just run a computer and pick the objects and then run the spectrographs to record the light from the objects and determine if the quality of that light has been recorded properly. So um, so that part has changed now in the last month and a half because we've begun to the resident astronomers. We work from home now. In fact, you can see in my home office. I just got off the telescope a few nights ago. I have these two sort of big computer screens that well, I had them illuminated, but they've darkened up. But you can see fairly large um, computer monitors that I just installed that are allowing me to run the many different pieces of software that we use to run the spectrographs. And so over the weekend, just this past weekend, I was observing for 4 nights, Friday through Monday night, and so I was running the spectrographs of the Hobby-Eberly Telescope from here at my home in my home office, and the telescope operators they still are up at the HET. They're in the control room there where they normally we both used to work together, but it's safer now to have one person at home observing and another person up at the telescope. We need that one person up at the telescope just because if an emergency situation occurred, he or she, and I say we have two of our telescope operators are women and two are men. And so, but they have to be there physically to handle an emergency situation,
To push the
whether it's
big red button if something goes wrong,
right
right?
to push what we call the emergency stop button or sometimes other things to physically take care of problems. So they have to be up there. But the astronomers now, we're just like most of the rest of the country. We're working from home, and so for the 4 nights over this past weekend, I was working here observing with the Hobby-Eberly Telescope. So it has changed in that respect quite substantially the way we do business.
Yeah, and unlike a lot of other telescopes, for the Hobby-Eberly, the astronomer who requests time with it doesn't actually physically come to the telescope, right? They send a proposal and then you get it for them, right?
That's right. That's right. In that regard, it's very much like using the Hubble telescope. You spend months writing a proposal, and then it gets judged by a time allocation committee. A committee that judges the quality of the proposal. And if you get the time, then you prepare another set of computer files that describe how the observations are to be made with the Hubble telescope. And then you wait months and months until your observations are taken, and then you get an email that says, "Oh, you have data, and here's how you get it." So most of the astronomers that use the Hobby-Eberly Telescope, it's that sort of same experience for them. They submit their program, and if they get the time, then they submit another set of computer files that describe the program, and then we use those to actually take the data. And so it's not quite like the Hubble telescope, uh, where you might have to wait 6 or 8 or months or a year sometimes to get your data. Usually, the Hobby-Eberly Telescope astronomers would wait a few months, at the most, because we work in 4-month segments. So, yeah, it's a very different operational telescope compared to most ground-based telescopes.
All right, well, that's about all the time we have. But thank you so much, Stephen, for joining me for this. This has been really interesting, and wish you the best at the ATT.
Well,
Hopefully, keep
Stephen,
having clear skies because the weather's been great lately. I know it's been great
yeah.
for you.
Oh, it's been beautiful. Yeah, and I really appreciate it. I had a blast doing this too. So I hope everybody has a good time out there in astronomy land.
Thanks. And I just want to add that if any of you watching this have any other questions you want to ask a professional astronomer, there'll be a link in the description below, and you can fill out your question, and we'll do more of these interviews. We'll ask other experts, and they'll take your questions. But again, thank you so much, Stephen. This has been great.
Enjoyed it.